I can see your screen. Okay. Thank you very much.
Good afternoon, everybody, from Vienna for this oral session 2.1 on characterization of treaty-relevant events. From Vienna, it is me, Mario Zampoli, and my dear colleague, Boxway Chu. We will be hosting you to this session. It is we're looking at a lineup of very interesting talks. The first 4 presentations will be in general on treaty-relevant events and the characterization. And there is going to be a kind of second part of this session because we have 4 talks that will address specifically the tragic explosion that happened in Beirut last year in 2020. And the analysis of data from that explosion, yield estimations. There's going to be a really detailed look into this event, which from the characteristics of the waveforms that it had, of course, fits into the description of this session. So this is going to be like a kind of dedicated sub-session to this overall session, which will be quite long. So I would say without further ado, I would like to introduce the first presentation, which is going to be given by Charles Carrigan on implications of underground nuclear explosion cavity evolution for radioxenon isotopic composition. So at this point, I would ask please to play that presentation. Thank you.
Hello to everyone. In this joint US-French study, we developed a new model to better understand how the physical evolution of the cavity following an underground nuclear explosion, or UNE, can potentially influence the evolution of radioxenon isotopes. We further looked at how the resulting cavity gas composition might affect the screening criterion for evaluating an atmospheric sample. Much of what I'm going to be talking about today was published in a paper appearing in the Journal of Environmental Radioactivity in 2020. A major objective of that paper was to better understand the potential differences between radioxenon detections caused by UNEs on the one hand and atmospheric background due to civilian sources such as nuclear reactors, research reactors, or medical isotope production facilities. We believe our model provides a framework for plugging in appropriate processes affecting cavity gases, particularly the composition of radioxenon, which is so important for IMS monitoring. In our work to date, we have found that the physical evolution of the cavity has the potential to strongly affect the radioxenon composition, as was originally suggested by Lars Erickiger in 2013. Taking into account the effects of cavity evolution produces isotopic signatures that are more distinguishable on the multiple isotope ratio chart, or MERC, than is predicted by current models. And finally, the potential exists to reduce some of the parametric uncertainty in these more detailed cavity evolution models, which require more parameters, by taking advantage of available seismic and known geologic data pertaining to the detonation site. Isotopic evolution models that depend only on a decay chain network, such as that of England and Ryder, have been typically used to predict the relationship between UNE signatures and background observations. An evolution model that is based only on the decay chain necessarily assumes a well-mixed and closed gas phase system during the decay of precursors into radioxenon. While this isn't wrong at all, such a model is, or should be thought of as, a bounding model and ideal in many respects. A more general model permits both partitioning of the radionuclide inventory within the cavity, as well as the loss of gases from the cavity. The modeling framework presented here links physical cavity evolution with xenon compositional evolution. In our more general model of isotopic evolution, there are several different phases of cavity evolution which are considered. While our model is supported by geological observations involving drillbacks into detonation cavities, we recognize that processes occurring in the cavity during a detonation can be incredibly complicated and highly variable, depending on a variety of initial conditions. At this stage, our model is general and intended to estimate the potential impact of physical processes on the gas phase signature. That said, the initial redistribution of radionuclide inventory begins during the cavity expansion phase, as represented in Part A of the figure, as both shock melting of the expanding walls and vaporization are occurring. During this phase of cavity evolution, we assume a bulk fraction of the total radionuclide inventory is separated permanently into the melt. We assume negligible fractionation of precursors from daughters occurs during this phase. The vapor phase contains refractory precursors which rain out in order of condensation temperature in Part B of the figure, which is already occurring only hundreds of milliseconds into the detonation. This is the first point in cavity evolution where fractionation begins to take place. As the cavity pressure falls further, more melt may explode off the walls as pore water superheated by shock melting turns to steam. The fragmented melt captures additional refractory precursors. In parts C and D of the figure, pressure falls low enough that the roof collapses and any remaining precursors are either lost into the melt or some may settle out on the surfaces of the rubble from the collapse, remaining in contact with the gas phase. Using the text boxes, we show here briefly our partitioning model, starting with bulk partitioning of the radioactive inventory, allowing negligible fractionation. Then, depending on a lot of different factors, what happens next either results in slow to no rainout of precursors or rapid rainout of precursors. For evaluating rainout of precursors, we have selected an example cavity cooling temperature plot on the left and included estimates of condensation temperatures. In the next slide, we will look at the effect of the refractory rainout process using this temperature profile and refractory condensation temperature data. In a variation of the four isotope evolution plot originally published by Martin Kalinowski and Christoph Pissner, we have added the predictions of our model. But first, there are a few things to explain. The evolution of the four isotopes is represented by ratios on the two axes of this plot. The first dashed line to the far right is the isotopic evolution path for the independent yield for radioxenon produced immediately at detonation. The second dashed line to the left, labeled ENR, is the evolution curve resulting from the decay chain network, with precursors ultimately producing the four radioxenon isotopes. To get this curve requires the assumption of a well-mixed and closed system. The red dashed line further to the left is the line typically separating UNE isotopic ratios from background isotopic ratios due to sources like nuclear power plants and medical isotope facilities. Now, the cyan-colored lines show what happens according to our rainout model. Faster rainout moves the curves away from the discrimination line and towards the independent yield line. Eventually, we run into a limit where even faster rainout can't move the curve further to the right. This is the limit here. To go any further requires a cooling curve with a faster temperature drop-off than the one we used in our model. According to Olson 1967, such temperature profiles may be attained following the detonation. This is a ratio plot using xenon 131M and xenon 133 that is suitable for tracking isotopic evolution for weeks to months after detonation. In this case, both partitioning and seepage influence isotopic evolution. In our model, yield can also influence isotopic evolution. We compared our model's predictions with the Russian observations shown here, almost 2 months after the DPRK 2013 event. The data was obtained from the 2014 paper by Ringbaum and his colleagues. What we found was the DPRK signature was consistent with an event between 1 and 10 kilotons if rainout effects were neglected in this case. The DPRK event has a seismic event estimate of around 8 kilotons, which we found encouraging because it fell between the 1 and 10 kiloton lines in the no rainout case. In this case, the permeability of the containment zone was set at the high end of measured values for containment zones when containment was considered successful. So what happens if we use a much lower value of permeability for seepage from the cavity? Here we use the low end of measured permeability that we have encountered in our previous experimental studies. In this model, the containment zone is only 1/10 as permeable as the case considered earlier. In the red box overlaying the original high seepage case, this box, we plotted the new results assuming the lower permeability, and here are the Russian observations. The inset shows that the low seepage has the effect of further separating the 1 in 10 kiloton rainout lines, with the observed DPRK ratios still remaining bracketed in these lines. With our colleagues at the CEA and IPGP, we considered whether gases produced by refractories that are partitioned from the melt at the cavity bottom might migrate back into the gas phase from the melt. We found that transport processes like thermal convection in the melt and scavenging of radioxenon by bubbles of exsolving volatiles were probably inadequate to significantly modify the isotopic evolution of the overlying gas phase in the cavity, given the time available and the degassing of the melt at early times during the pressurization of the cavity. As the photos show, we also evaluated the possibility that cold rubble falling into the cavity or into the melt might enhance pathways, which it appears to do through the formation or through decomposition and the occurrence of fracturing. Well, our experiments exhibited some of the interfacial characteristics observed in photos of the intermingling of roof rock and debris in the 1957 Rainier UNE. We still did not identify an adequate mechanism for moving xenon back into the overlying gas phase. I think the main points to take away from this talk are that models of isotopic evolution that depend only on the decay chain network are likely to be somewhat idealized according to our study. However, they still represent a very useful bound that is relevant to distinguishing UNE signatures from civilian backgrounds. More detailed models that couple cavity evolution with isotopic evolution seem to predict evolution curves that are easier to distinguish from civilian backgrounds. And I think our model also suggests that cavity collapse will complete partitioning, and the time of collapse from seismic observations may be useful for producing a bound to the right of the ENR evolutionary curve. And finally, yield-based estimates of radioxenon production will tend to be overestimates due to the fact that we have initially partitioned some significant bulk of the radionuclide inventory into melt, which is not accessible to the gas phase. And that ends it. Thank you.
Thank you, Charles. Thank you for this very interesting presentation. Just asking, so far there are no questions from the audience. So therefore I ask if any of the speakers who are present wish to ask a question. By the way, I note that all speakers seem to have their camera off. If you wish to turn on your camera so we can see each other. Well, then I may ask, oh, there is one question here. Okay. It's being passed on to me. So the question is from Robert Anevanta. Would your model be able to quantify the impact of a water table above, below, and would that have a significant effect on your results?
Can you hear me first of all?
Yes.
Okay, no, that's a great question. And the answer is that there are many possibilities that would have to be considered. The presence of a water table might well indicate that there's a lot of pore water in the rock, of course, and that during the compression phase in the early part of the detonation, as the cavity is being created, basically you get a lot of compression, a lot of heating, and the presence of pore water, of course, as the pressure falls off, can turn to steam and literally blow the magma or the lava or the melted rock off the wall. And that will actually have the effect of improving the partitioning of the refractory precursors. So the answer is that could have an effect, yes. Basically, a dry environment could behave differently from a wet environment for doing a nuclear test. That at least is my preliminary answer to this question. At least this is what the model would predict.
Thank you, Charles. There is another question that comes from Yochai Ben-Horin. How did you calculate the chances that xenon to be released?
Okay, what we're doing here in the case of the modeling of the gas phase, we basically are not looking at the release of the gas so much as the composition of the gas in the cavity. The presumption is that during a prompt release, a rapid release where you have basically a large pathway to the surface, the gas would be relatively unchanged and the composition would be relatively unchanged. That's not necessarily true for a very, very slow release. of gases, what we might call a delayed release, where the gas spends a lot of time in the containment zone. So I hope that helps. I hope that answers the question.
Thank you. Is there another question? No. No. Okay, so wonderful. Thank you, Charles.
Thank you very
for
much.
the attendees who asked the questions. I think now we are ready to prepare for the next speaker. Will be Josef Christek, I think is the main presenter of this. And it is on detecting underground cavities due to underground nuclear explosions using seismic ambient noise. So please, if you can play the video, thank you.
Hello, my name is Josef Christek, and I'm going to talk about work we did in collaboration with my colleague Miriam Kristekova, Peter Moco, and Peter Labak. I will present a new method for detecting and locating a horizontal position of underground cavity, which uses finite interval spectral power, computed from the seismic ambient noise measurements. The identification and location of cavities generated by an underground nuclear explosion is an important proof in case of suspicion of violating the Comprehensive Nuclear Test Ban Treaty. I will start with motivation, then I will introduce the finite interval spectral power method, I will show the application to a real site, and finally I will say conclusions. Our work was motivated by efforts to develop CTBT on-site inspection capabilities to detect and locate cavities caused by underground nuclear explosions. Such cavities with diameter of several tens of meters are located in depths of possibly several hundreds of meters. The on-site inspection team has limited time for inspection, so it's impossible to rely on earthquake records. The team has limited number of seismic stations and limited possibilities to deploy large and dense array. Therefore, it's important to have a robust method based on analysis of seismic ambient noise. Let me briefly explain a principle of our finite interval spectral power method. Consider a free surface site with some underground geologic conditions and the corresponding spectrum of noise. The spectrum may have peaks representing local amplification of noise. In case of laterally varying conditions, the peak frequencies can change from receiver to receiver. Presence of cavity will cause appearance of additional, relatively small spectral peaks, but at many frequencies. The presence of spectral peaks due to the cavity and spectral peaks due to the surrounding heterogeneity in the spectrum of noise can make it difficult to identify origin of individual spectral peaks. Instead of problematic identification of individual weak peaks and calculation of corresponding spectral characteristics, it may be advantageous to use a spectral characteristic comprising a finite interval of frequencies. Therefore, we propose to evaluate the spectral power representing the entirely reasonably selected frequency interval Fmin Fmax. The vertical Fisp is defined as a finite integral of smoothed power spectra of the vertical component. The horizontal Fisp is defined from the geometric average of spectra of two horizontal components. Finally, we can also define a horizontal to vertical ratio of Fisp. There are two aspects of the method. The first is how to determine values of minimal and maximal frequencies. The second is how to correctly estimate power spectral density. How to determine frequencies Fmin and Fmax? Very small values of Fmin would potentially lead to including effects of medium much larger than the cavity. Too large values of Fmax could potentially lead to sensitivity to heterogeneities significantly smaller than the cavity. If the size of cavity is unknown, Fisp should be evaluated for several trial values of Fmin and Fmax. Usually, the power spectral density is evaluated under assumption of almost stationary noise. The noise record is divided into segments at which the power spectrum is computed. Finally, the obtained spectra are averaged. In case of ideal stationary noise, all segments would have the same spectral properties. If the ideal noise is weakly disturbed by, for example, anthropogenic activities, Then the different segments will have a little bit different power spectra. Statistically, we can describe the power spectra of almost stationary noise by a log-normal distribution. Recall the asymmetry and skewness of the log-normal distribution. The mean, median, and mode are different. The maximum of the probability density function is at mode, that is, the mode is the most probable. Considering the log-normal distribution of power spectra of segments, the mode is the best characteristic of the almost stationary noise. Therefore, instead of averaging, we are using the mode as the estimator of power spectral density. The coefficient of variation quantifies the differences between the segments regardless of the value of PSD. The inverse of coefficient of variation defines signal-to-noise ratio. The larger signal-to-noise ratio, the smaller differences between the segments, and therefore more reliable measurement. Having estimated power spectral densities as mode of PSDs of all segments, we could evaluate the finite interval spectral power. However, we propose to evaluate Fisp at each time segment. Then, similarly as in the case of PSDs, we evaluate the Fisp as the mode value of Fisp of all segments. We can also quantify reliability using signal-to-noise ratios. For application of Fisp, we assume a set of measurement points at the free surface above a suspected cavity. We don't require any specific array configuration. We assume sufficiently long three-component records of noise at all measurement points. To be consistent with the assumption of the almost stationary noise, it's necessary to check quality of noise records and select only those segments with similar characteristics. In other words, we need to identify and exclude the outliers. Here we see an example of manually selected segments using geopsy software. The manual selection is a very tedious process. Therefore, we found a new method of automatic identification of distorted time segments. The procedure is as follows. Division of the noise record into half-overlapping time segments and application of Welch window to each segment. Computation of power spectrum of each segment. Smoothing of power spectrum of each segment. Computation of spectral power of each segment. Identification of outliers by applying Tukey's fences to the logarithm of spectral power. Removal of outliers from the set of the time segments. Repeat step 6 and 7 until no outliers remains. Now I will show you the application of the Fisp method to the real site. The team of CTBTO experts performed extensive geophysical measurements in the area of Great Cavern near the small village of Elshepeten. Our goal was to identify horizontal cavity position based on seismic ambient noise recorded on ground surface. The Great Cavern has a roughly oval shape with a horizontal diameter of 28 to 30 meters, height of 25 to 28 meters, and sailing approximately 70 meters below the free surface. We were provided with continuous three-component records of noise at 50 measurement points. The area was roughly 400 meters times 450 meters. The interstation distance was around 50 meters. The cavern is just in the center of the area of interest. Here is an example of 24 hours of three-component noise data at the central measurement point. The noise record exhibits transients and day-night variations. We divided the whole record into 50 seconds time segments with 25 seconds overlap. On the bottom we see the logarithm of the spectral power of each time segment of the east-west component. The statistical distribution is on the left-hand side. We see that it is skewed and far from normal. The red line indicates Tukey's fences. The procedure clearly indicates non-stationarity of noise. For the Fisp analysis, we selected a relatively quiet 6-hour window. We again divided the whole record into 50 seconds time segments with 25-second overlap. The statistical distribution of spectral power is now close to log normal. The outliers, indicated by red dots, were removed from the set of the time segments. We process noise data from all stations and estimated power spectral densities. Here we see the plot of horizontal power spectral densities for all measurement points. The bold line indicates the measurement point just above the cavity. The dotted line indicates obvious outliers among all measurement points at which there were some problem with instruments. On the right-hand side, we see the corresponding signal-to-noise ratios. The larger signal-to-noise ratio, the smaller differences between the segments, and therefore more reliable measurements. PSDs above 30 Hz are more scattered because PSDs at higher frequencies are likely affected by heterogeneities smaller than the cavity. PSDs below 5 Hz could be more affected by medium much larger than the cavity. In this interval, there are several curves that differ from majority. This could be the potential effect of cavity. Also, the signal-to-noise ratios have the largest values here. Look at the distinct and sharp minimum at 5 Hz. We have found out that at almost all measurement points, there are several time segments with much lower amplitudes at 5 Hz than in other segments. This indicates anthropogenic origin of the peak in PSD at 5 Hz. Therefore, the frequency interval for calculating Fisps shouldn't include 5 Hz. We selected interval 5.5 to 30 Hz. Obviously, the selection of the frequency interval is approximate. Therefore, we calculated Fisp also for a wider interval 2 to 30 Hz. The calculated Fisps are visualized in form of maps. Maps show horizontal, vertical, and horizontal to vertical ratio Fisps for two frequency intervals. We clearly recognize localized anomalous patterns in maps of horizontal and horizontal to vertical ratio Fisps. The center of anomalous pattern in the frequency interval 5.5 to 30 Hz agrees with the horizontal position of the center of the cavern. In case of wider frequency interval, the center is shifted. As I mentioned earlier, we prefer frequency interval 5.5 to 30 Hz because inclusion of lower frequencies considerably enhances the effect of the medium. Conclusions. We present a new method which uses the finite interval spectral power of seismic ambient noise for detecting and locating a horizontal position of an underground cavity. The method assumes a set of potentially irregularly distributed measurement points in the area on the Earth's free surface over a suspected cavity and sufficiently long three-component records of noise of all measurement points. The records should be obtained in similar conditions, but they can be performed sequentially. We tested applicability of the method using records of seismic ambient noise obtained during the field test in Felshepeteni in 2019, the karst and clay mining area. The noise was recorded at 50 points distributed in the area over a known cavity with the ceiling at 70 meters depth. Using our method, we were able to locate the horizontal position of the cavity in the aerial maps of the finite interval spectral power of the recorded seismic ambient noise. The method is ready for further tests in different cavity conditions and applications. The presented method was published this year in Geophysical Journal International. Thank you for your attention.
Thank you, Josef. Very interesting presentation, very interesting work. While Boshwe is... there is no question yet? Okay. Does any of the other speakers in this session have questions that they would like to ask? One? Then I would like to ask a question. Well, actually, maybe it's two questions. The first question is, so the characteristics of the noise field that you're assuming here is a diffuse noise field. Correct?
Yes, you are right. We assume diffuse noise field or stationary noise.
Okay. And I was wondering, have you tried to see how your technique relates to techniques for imaging or tomography, passive tomography that are based on cross correlation between the different sensors?
No, we didn't check this because yeah, it's not so a large amount of data. We have just 1 week of data, and we are not sure whether this is enough for this cross correlation technique.
Oh, interesting. Thank you. Well, I would like to say that several applications of passive imaging by cross correlation highlight that the cross correlation emerges actually quite rapidly. Maybe it could be something to look at.
We can try, maybe.
It's very interesting. Any other questions? No. Thank you so much, Joseph. Very interesting presentation. So at this point, we're ready to move on to the next speaker, who's Marian Kalon, and the presentation will be on matching electromagnetic measurements to infrasound signals. So please, if we can play the presentation.
Hello everyone, my name is Marian Kalon and I'm going to talk about data fusion between infrasound and electromagnetic pulse, which is part of my thesis in Tel Aviv University in cooperation with Sorek Nuclear Research Center. The thesis was supervised by Azi Lifshitz, Coleman Price, and Anthony Weiss. The goal of the research was to examine the possibility of improving the analysis process of atmospheric infrasound events under the CTBT. We suggest to do so by fusing infrasound and electromagnetic pulse signals. When the rationale is that nuclear events emit both infrasound and IM signals, and as far as we know, no other infrasound source, apart from nuclear events and volcano eruption, that emit both infrasound and electromagnetic signals. Therefore, if we have an infrasound event which is not associated to an electromagnetic event, we know that it is not a nuclear event and therefore does not require any further analysis. The problem is that most common EMPs are generated by lightning. There are 45 lightning per second occurring on Earth, and it may cause a coincidence of infrasound event, which is associated to lightning event, and it may confuse us to believe that it is a nuclear event. Thus, we suggest the following methodology. First, we want to know how many infrasound events do coincide in time and direction with electromagnetic events. Assuming that there are such events, we want to know if we can identify those events as lightning or not. If they are lightning, then we can eliminate the infrasound events as nuclear. If they are not lightning, then the infrasound events require further analysis. The infrasound data was taken from cell 3 from 36 non-consecutive days. We took full days, meaning we had data from day and night, and from different seasons, winter, summer, etc. Overall, we had 580 events. Here in the map, we see in red the location of the electromagnetic station. In black, we see the location of the infrasound events from the cell 3. Of course, that we took only the events in the reception range of the electromagnetic antenna. The EM measurements were taken from single station, as we saw in the map. The station consists from one component of electric field and two perpendicular components of magnetic fields. The measurements were taken from the same 36 days as the infrasound data, and we detected about 5 million events. Here in the figure, we see the electromagnetic measurements, and the red lines are the detected electromagnetic events. Then we took a time window around each infrasound event, and we saw that all infrasound events coincided with several EMPs in time. When we also considered the direction of arrival of the infrasound and the electromagnetic events, we saw that in about 50% of the cases, the infrasound event did not coincide with any EMP in time and direction. We can also see it in this histogram. However, the other 50% of the cases, infrasound events did coincide with several EMPs in time and direction. And thus, we need to identify those electromagnetic events as lightning or not. Therefore, we used machine learning techniques. Machine learning requires labeled data, and we want to classify the electromagnetic measurements as lightning or nuclear explosions. For the nuclear explosion group, we simulated nuclear explosions. For the lightning group, we took our measurements. When measurements that had correlation higher than 80% with lightning simulations were chosen to be in the lightning group. Here in red, we see an examples for measurements of lightning. Here in black, we see an examples for simulations of nuclear explosions. From both electromagnetic measurements and simulations, we extracted 19 features. The features were taken from time domain, frequency domain, and from a spectrogram. From now on, each event, each signal is represented as a dot in the 19-dimensional space, which is the featured space. And we use principal component analysis, PCA, for dimension reduction. When PCA is also an unsupervised method, meaning it doesn't have any pre-knowledge on the data. And we see here in the 3D graph that the PCA were able to separate between the two groups of lightning and nuclear explosions. Then we use for classification k-nearest neighbors algorithm. K-nearest neighbors calculates the k-nearest neighbors of a new event that arrived to the PCA space. And according to the majority rule of the neighbors, it determines the classification of the new event. Here we see the model validation. First, we see that we had 0 misdetections, meaning non-nuclear explosion was classified as lightning. However, we did have 17 cases of lightning, which the algorithm classified as suspected nuclear explosions, meaning that if those lightnings, if those EM events were associated to an infrasound event, this means that those infrasound events would require manual analysis. However, this is not the case, and we had overall very good classification rates. And we saw that when we took the electromagnetic events, which coincided with infrasound events in time, and we projected them to the PCA space and classified them, all the EMPs were classified as lightning, meaning no infrasound event required further analysis. No infrasound event required manual analysis. This table summarizes the results. We see that we started with 580 infrasound events. All of those events matched in time with electromagnetic events. About half of them matched in time and azimuth. However, none of them required manual analysis because all of the electromagnetic events that associated with the infrasound events in time were classified as lightning. To conclude, we saw that time and azimuth fusion between infrasound and electromagnetic pulse is not sufficient to eliminate most of the infrasound events. However, when we use machine learning techniques, we can discriminate between lightning EMP and nuclear EMP, and we can improve the analysis process of the infrasound events under the CTBT, which is the goal of the research. This research is an ongoing research. The future work includes first real-time data fusion in the single station level. We placed our electromagnetic station in close proximity to the infrasound station in Meron, Israel. Then we want to achieve a more accurate detection and location by using multi-station system. One of the options is to cooperate with existing lightning detection networks such as Woolen. And for last, we want to train the machine learning model on a larger data set, mostly data set of more simulations. And that's all. Thank you all for listening. If there are any further questions, I'll be happy to answer them. Thank you.
Thank you, Magda. Very interesting presentation as well. Are there any questions from the audience? Not yet. Any questions from the other participants in this session? And at this point, I have one curiosity, and that is, what is the detection range that you see for a network that would be monitoring the EMPs as opposed to the infrasound network? Because infrasound can, of course, travel very, very far. For the case of the lightning and for the case of the nuclear explosion, what do you see as the detection ranges, the distances over which you can detect such signals? Oh, you are muted. You need to unmute yourself.
Okay. So our plan is to place the electromagnetic station close proximity to the infrasound stations. So if an event will occur and we will detect it in the infrasound, we will see it as well in the electromagnetic station. Therefore, if we do this fusion between the electromagnetic and the infrasound, we will be able to see an event that occurs in both of them, and to eliminate an event that occurred in the infrasound but did not had an electromagnetic pulse that was associated with.
Okay, thank you. There is a question from Joachim Ben Horin, and that is, how did you perform the simulation?
Okay. The simulations are composed of two parts. The first part is the source term, and the other is the propagation. The source term was calculated based on Longmire theory, and using FDTD, which stands for finite different time domain. We calculate the electric and magnetic field in presence of charges like electrons, positive and negative ions. And then we integrate on the space to get the initial condition for the propagation. And for the propagation, we use the LWPC package, which stands for long wavelength propagation capability, to calculate the propagation in the Earth Unisphere waveguide.
Okay, very interesting. So can you just tell me, and that's another curiosity of mine, over what distance do you detect the lightnings with these lightning detection systems?
Around 2,000 kilometers.
Wow, that is impressive. So you mean that is with the EMP detection?
Yeah.
Wow. So it is very long propagation.
Yeah, it's a very long range, and it enables us to see a big picture, even if we had one station.
Yeah. Wow. That's that is completely. I'm not an expert in that field, and it's amazing to with EMP it can be detected from so far away. Any no? Any of the other speakers wish to ask a question? Oh, is there anything else that you would like to add, Marjan, before we move on?
We do plan, as I said before, that maybe we can implement this to make the we do want to collaborate with lightning detection networks in order to see if we can eliminate infrasound events by just fusing between those lists and the cell tree list. We are planning to check this soon and see if we can help.
Yes, that's very interesting, because some things that can reduce greatly the workload, it can be ruled out so at the very early biological processing. Yes, in our field, with the field that I work in, which is underwater acoustics, there are events, for example, seismic surveys for oil exploration, things like that, which produce signals that tend to be detected by the network and require often human intervention to rule out that the series of signals is not a relevant event. So yes, these are very important contributions, because now that the network is bigger and bigger and we see more and more data, it becomes really important to not drown in all that data. So these kinds of techniques, like what you are showing, are very relevant, very important. And here mixing, of course, with electromagnetic part, which is something that is not part of the IMS core technologies, is very interesting, very fascinating.
I agree.
Thank you. So at this point, we move on to the last presentation about the pretty relevant events that are not related to the tragic Beirut explosion of last year, which will be really the second part of our session. And yes, this presentation is from us here at CTBTO. So please, if I can ask my colleagues to please play the video. Thank you. This talk presents detections of primary and tertiary phases associated with the 6th DPRK underground nuclear test made with hydrophones of the hydroacoustic component of the International Monitoring System. Presentation was co-authored with my colleagues Peter Nielsen, Ronan Lebras, and Paulina Bittner, who are in the IDC, and Yorgos Haralabous and Jerry Stanley, who are in the IMS with me. All 6 announced DPRK underground nuclear tests have been detected by the IMS since 2006. The event that we focus on in this presentation is DPRK6 from 2017, which had numerous seismic detections and 1 infrasound detection, and also 2 automatic hydroacoustic detections, which caused us to look more in detail into the events. And indeed, as you will see in the presentation, there has been more to this than just these 2 detections. This view graph shows in the map the CTBT monitoring system, international monitoring system, with all its 337 monitoring facilities of the different technologies shown on the legend on the left. The rate of completion as of today is quite high, since 302 of the total 337 monitoring facilities shown are completely certified. The focus of this presentation is on the hydroacoustic component of the IMS, and namely on the hydrophone stations, of which there are 6. And these are AJ03, Juan Fernandez Islands, Chile, AJ10, Ascension Island, AJ04, which is Crozet, AJ08, which is Diego Garcia in the Indian Ocean, AJ01, Cape Lewin, and AJ11, Wake Island. The hydroacoustic hydrophone stations comprise triplets of hydrophones, which are suspended in the water column by riser moorings that are kept in place by floats which remain submerged, and the hydrophones are connected to the shore facility by fiber optic cable, and the data received from the hydrophones is then sent to the IDC in Vienna by satellite link. The image on the top here shows an example of one of our hydroacoustic stations, the triplet to the north of an island and the triplet to the south. Primary phases from the DPRK6 event were detected at the stations shown in green on the map. The continuous circles denote automatic detections of the P phases. The dashed green circles denote manual detections, meaning ad hoc processing was done by us. And these detections were not made by the automatic IDC processing pipeline. In red circles are the stations that did not make a detection, either manual or automatic. To be noted also that H11 had a manual detection of a tertiary phase, of a T phase. Time series for the P phase arrivals from this event are shown in these plots on the right. On the top, we have the automatically detected arrivals. And on the bottom, we have the manually detected arrivals with the ad hoc processing made by us. It can be seen quite clearly that the arrivals exhibit the sharp rise time and exponential decay of the P phase from the not natural events underground. It is also curious to note that the events which were manually detected had actually a rather good signal to noise ratio. This is something that would be interesting to look at more in depth in the future. The calibrated spectrograms for the arrivals that we have seen on the previous slide at H01, H11, H08, and H03
are shown in this slide. In all cases, the arrival of the P phase can be recognized quite clearly in the spectrograms. Seismic ray paths between the source and the receiver were obtained with the Tau P toolkit and the Earth model that is implemented in it. The travel times were also obtained, and consistent arrivals with the travel times are obtained in the different cases that you see here. For H01 West, it's this P phase shown in red, and this number here shows the angular distance. For H11 South, it is this P phase. Where there were no signal detections, namely H04 North and H10 North and South, respectively, these detections were not possible either automatically nor manually. And it turns out that these two stations lie in the shadow zone of the core phases, which are in the range between 104 and 140 degree distance. So the fact that the paths here are in red is that these would be the plausible paths, but no detections could be made because the energy was just not sufficient at the receiver. The seismic ray paths for the manual analysis are shown here for H08 and for H03. The one for H03 is certainly the most interesting one, since the arc distance is basically between source and receiver at the antipodes. And in red, you can see the path of the PKP phase that was detected in H03 Chile. One important parameter which allows to characterize an arrival as a P phase as opposed to a hydroacoustic phase is the apparent horizontal wave speed. That is the difference in time of arrival of a wavefront between hydrophones in the triplet. And from this time difference, one can obtain an apparent wave speed. Now, a hydroacoustic phase would be propagating almost horizontally or with rather shallow angles in the water column, and therefore the speed calculated from the inter-hydrophone arrival times would be very close to the speed of sound in the water, which is about 1.48 kilometers a second. However, P phases, which travel through the Earth, couple from the Earth into the water at a rather steep angle, not far usually from the hydrophone array, and therefore the arrival at this steep angle will lead to much shorter inter-element arrival times between the hydrophones, and therefore will lead to apparent horizontal wave speeds that are much higher than the speed of sound in the water. The direction of arrival and the apparent horizontal wave speeds were computed with the progressive multi-channel correlator DTK GPMCC for all hydrophone triplets where the DPRK6 event was detected either automatically or manually. Here you can see at H11 South, the arrival detected the back azimuth given by the colors here over the different frequency bands, and in this case, the horizontal wave speed, which you can see from the color scale is rather high. Indeed, here the back azimuth points in the expected direction of the DPRK6 source location, and the apparent wave speed is rather high with a median of almost 17 kilometers a second. So it's basically more than 10 times higher than the speed of sound in the water. In red is shown the small and certain clear ellipse, and with the star in the middle, which is the REB location, obtained from the 125 seismic station detections. The detections made with the hydroacoustic triplets with which the DPRK6 event was detected automatically and manually gave this location, which is only 27 kilometers from the RAV event location, and has this uncertainty ellipse shown in turquoise color. The second part of this presentation focuses on the tertiary phase. So it is plausible that a tertiary phase, so-called T phase, could have been excited in this manner, as shown on the slide. The underground event here sends out a P phase, which at the east of the Japan Trench casts a hydroacoustic wave in the SOFAR channel, which can reach HA11 over here. Indeed, this slide shows ocean bottom seismometer recording from the Japanese SNET and DONET tsunami warning systems, which recorded seismic arrivals consistent with a P phase, with propagating from DPRK6 to these locations. These were presented by these researchers from Japan. A close analysis of the hydrophone recordings at H11 showed indeed an arrival, you can see here, of what could be consistent with the T phase from the DPRK6 event. And the north triplet in this case could also see a regular repeating pattern of noise from a seismic survey. Cross correlation gives back azimuths for H11 north, which indeed points in the correct direction towards possible T-phase coupling location. And here you can see for the remainder of the cross correlation analysis, the arrivals from the geoacoustic survey from the north. At H11 south, signal consistent with the T-phase arrival can be recognized more clearly, as the south triplet is not as much affected by the geophysical survey that is seen on H11 north. Also in this case, the cross-correlation analysis gives a back azimuth, which is consistent with the hypothesis of the T phase. And indeed, by drawing geodetic rays back along the back azimuths obtained by the cross-correlation analysis, one obtains a point which fits very well into the location here on the east coast, near the east coast of Japan. And if one makes the hypothesis of a P phase propagating from the source to the east coast of Japan here, and then coupling into a hydroacoustic wave to the two stations, the arrival times obtained are quite closely consistent with the arrival times that would be predicted using the ERSPAIN 91 travel time model. In conclusion, all 6 announced DPRK events since 2006 have been detected by the IMS, as is known. DPRK6 was detected by a multitude of stations, which include, for the first time to our best knowledge, hydroacoustic stations. Indeed, 6 hydrophone triplets, including 2 of which had automatic processing detections. The localization of the event origin location by the hydroacoustic stations using P phases compares rather well with that obtained by the seismic stations. In addition to this, the Wake Island hydrophone station, HA11, recorded a signal that is consistent with the T phase generated on the southeastern Japanese continental slope and attributable to DPRK6. It is interesting to note that further studies are required to investigate which criteria in the automatic processing triggered hydroacoustic automatic detections and why HA03 and HA08, which has had a rather high SNR in the arrival, did not lead to an automatic detection. This presentation shows also how sensitive the IMS hydrophone stations are, as what can be seen, for example, from the detection at distances up to 17,500 kilometers from the source of the P phase from DPRK6. Thank you. And this concludes my presentation.
Well, thank you for listening. At this point, we have quite a few minutes to go until the next talk. Would like to ask if any of the other colleagues here connected in the WebEx session as speakers has any questions about this. Okay. Yes, please.
Yes, I do. Which parameters go in the identification of this hydroacoustic phase? So is it the timing? Is it the direction, the velocity?
There are a number of things that go into it, and it is the bandwidth, for example. There needs to be broadband. It needs to be short, pulsive. So it's time duration. Rise time. There are a number of parameters that go into that. Actually, if you look back at the presentation by Ronan Lebras, the invited one yesterday, he shows all the criteria that go into defining hydroacoustic phase. Well, if it is a P phase, of course, you need to have also the velocity. That is the very important parameter, because that is much higher than the velocity of a hydroacoustic phase. The apparent velocity of a P phase between the hydrophones comes from underneath. However, that is something that we will need to look into, I think, and revisit a little bit, because it is a bit so it is quite surprising that we could not get automatic detections for H08 and HA03, which had really very good signal to noise ratios, with a nice steep rising front and then an exponential decay, as you would expect from a P phase that is generated by an underground explosion. So I guess since we have this to our best knowledge, is the first time that we detected an event like this from the hydroacoustic network, the hydrophone network. And so we don't have many other cases to look back at and learn from. But we will need to try to understand why these other two stations that really had a signal to noise ratio that was superior to the ones that actually had the automatic detection, what led to that. So we are going to look into it some more. And then maybe also go back and look at historical data from the other tests and see if there's anything, at least at Wake Island, that could be picked up. Oh, yes, the question of how the primary phase can be detected. Yes, the point is that the primary phases that we detect on the hydrophones, so not these are not seismometers, they all come from underneath the triplet of hydrophones, and they couple from the seafloor into the water and launch a wave that propagates in the water. And so it is apparent horizontal wave speed, or you could say that the reciprocal of the slowness that we use there to understand that it is P phase. And oh, two more questions. Oh wow, this is almost going too deep. So about ground to water coupling, which seismic phase is the most likely to couple regarding the T phase detection? Well, it is going to be so the T phase is a wave in this case that is detected as a hydroacoustic wave that propagates in the sound channel and was launched by a vibration of the ground, seismic vibration of the ground at the depth where the SOFAR channel is, near the SOFAR channel axis. And that would most likely be a primary wave that launches this. It's the normal, in order to launch a wave from a solid, where you have three displacement components, into fluid, where it's a pressure wave, you need a vertical component, because the condition between, if I do it like this, the condition, boundary conditions are continuity of normal displacement, normal acceleration between the soil and the water, but there is a slip condition, so tangential slip is allowed if you don't assume viscosity in the fluid, and therefore what you need is a vertical displacement component that vibrates and shakes the soil. So that's why you have a continental slope most likely, and that continental slope is vibrating, has a normal vibration component that generates a hydroacoustic wave that propagates in the water column. Then there is another question. The SNR was high for some of the DPRK 6 Have you looked at 4P at hydrophones on the previous? Well, yes, that's from David Bowers. Thank you, David. I think that we looked with Peter Nielsen and Ronan and Paulina. They looked at some of that when we saw these detections. But again, I'm not sure if I think it's probably worth the while to go back and look at it more in detail to try to understand, maybe by manual processing and looking at the expected arrival times if there is nothing back there. So that is probably something that would be nice to look into. Thanks. Any other questions? No? Okay. Great. That leads us then right into the next phase of this session, which has 4 talks that are dedicated to analysis of the event on the 4th of August last year in Beirut. And so without further ado, I would like to play the first presentation from Laurent Guillot, please.
Good afternoon, Laurent Guillot. I'm working for the CEA, the French Atomic Energy Commission. I'm going to present you a work dedicated to the estimation of some parameters related to the Beirut explosion using only seismic data and seismic modeling. This work has been done in collaboration with Gaël Burgos and Johan Cano, who also work for the CEA. So what about the explosion? It was a massive above-ground explosion that occurred at the beginning of August in 2020 in the port of Beirut and led to extensive damage, as you can see it on the 2 photographs here that present a differential view from the sky, and also, unfortunately, many casualties. It seems that this disaster is due to the explosion of around 2.75 kilotons of ammonium nitrate, which is a fertilizer, and which was stored in a warehouse in the port. And this is not the first accidental explosion of that kind in the human history. We have, for an example, like the explosion and of the BASF factory in Germany at the beginning of the 19th century, or the AZF explosion in Toulouse in France. And considering all these previous explosions, we can obtain finally some kind of approximation for the efficiency and TNT equivalence of such of the explosions for such material. And in fact, it seems that 1 kiloton of ammonium nitrate is equivalent to the explosion of 0.42 kiloton of TNT. It seems that approximately between 50% and 70% of these fertilizers have been contributed to the Beirut explosion, and as a first proxy, finally, we can find a yield which is comprised between 0.5 and 0.8 kiloton. And in this presentation, we're going to introduce an analysis which was realized by by some CEA members in the weeks following the event, using only seismic data in order to obtain independent yield explosion estimation. You can also use other technologies like the infrasound analysis for this explosion yield estimation, and this is reported, for instance, on the Julien Vergou's poster. Julien Vergous is also a CEA member, and you have the number of his contribution on this slide. Quite quickly on this slide, there are many stations in the neighborhood of Beirut, and that allowed us to obtain a quite good localization for the event using only seismic properties and seismic data. And if we take a look at one record, for instance, at the Emps station, which is located approximately 100 kilometers due south to Beirut, and proceed to a multiple band analysis, and this is shown in the middle of the slide. You can observe in the high frequency domain amplitudes for the PG waves that are much larger than the SG waves. This high P over S ratio in the high frequency band is characteristic of an explosion. And so is the presence of large RG surface wave in the low frequency band. This is also the case for the quasi-absence of SH wave and love waves. Next slide. These photos can be validated using some discriminants like the MB-MS Vmax screening criterion. It's quite difficult to calculate the MS Vmax in that area for that event, because the relay waves are quite mixed with the SV waves and the S waves that are vertically polarized. The two wave trends are not well separated. That means that the measurement of the MS Vmax is not that meaningful, but we can obtain two stations values for the MS that are approximately equal to 2.1. We can see that on the next slides. We can also have information on 1 MB magnitude, which is the MB magnitude related to the PN phase, which is the P phase. Refracted at the interface between the crust and the mantle, and this MB magnitude is equal to 3.7. That means that finally the criterion MB MS Vmax is equal to minus 0.75, which is an indication of an event which is something like an explosion. On the next slide, we can also use very empirical calibration to estimate the yield. I won't give a lot of details on that slide, but for the French NDC, for the French National Data Center, we have magnitude, local magnitude, which is equal to approximately 3.8. Then corresponds to a yield equivalence in TNT, which is equal to 0.38 kiloton, which is approximately equal to what we have found previously. And what it's also interesting is that depending on the institute or the magnitude type, local magnitude or duration magnitude, we have very different estimation for the yield. Another way to estimate the yield is to use the Seismo-acoustic paradigm. What does it mean? The first time you consider that your source is underground, and you can use a classical model like the Muller-Murphy one, or more recent one like the Walter and Ford model. Put your source at depth, the standard scale of burial, for instance, and calculate the spectrum associated to a certain phase, like the PG phase. And then, of course, you consider that, like in the case of Beirut, you don't have an underground explosion, but an above ground one. And so you have to correct for you have to find a correction factor for the for this approximation and to obtain good results. And this was done by some people at the Lawrence Livermore National Laboratory, like Sean Ford or Michael Pasianus. In fact, they use real experiments to find some coefficient, scaling coefficient, that can relate the displacement, scale displacement, that would be obtained in the ground for a source that is underground or a source that is above ground. And there is a relationship between both. And finally, using this and correcting the Walter-informed spectra for an underground explosion, you can try to estimate the yield. This is done on the figure on the left of this slide, and considering a native burst of approximately 2 meters, you can find a yield that is between 0.2 and 1 kiloton. Now we go from the classical 1D model to 3D ones and simulation associated. And the first work we have realized was to invert for source mechanism using waveform modeling. And the 3D model we have used is that of Cavities and co-authors. You can find it on the slide. It is a surface wave model defined until frequencies of approximately 0.2 Hertz, I think, using classical cross correlation of seismic ambient noise. In the first stage, we use this model to obtain an equivalent 1D model using the classical path averaging between source and station. And the idea was to retrieve the best source mechanism by fitting waveforms of data and synthetics, which is shown on the right part of the slide. Not surprisingly, the best source mechanism is a subvertical force. The fit, in fact, is quite good, but in fact, the scale function in order to align amplitudes of data and synthetics is very different from the one obtained by foreign collaborators in 2014. This is a problem with the averaging of our elastic properties in the 3D model. Not sure. Perhaps the fact that we work between 5 seconds and 10 seconds, and whereas foreign and co-author gave formula between 1 Hertz and 5 Hertz. Second trial in a 3D model, again the Cavities model, and but this time without any averaging of seismic properties at depth, and we have the topography, but there is no water and no atmosphere, so in fact there is no seismo-acoustic coupling. The source is an explosive one, an underground explosive one, with Walter-informed model, for instance, with periods between 1 and 25 seconds and a yield of 0.5 kiloton. The runs that are obtained using a spectral element solver. After 30 seconds of propagation, you can see this on the figure on the right. You can observe a lot of wiggles that are in fact PNS waves that are diffracted by the topography or the underground heterogeneities, and very energetic wave fronts, which is a mix between relay waves and S wave. Sorry. Now you can observe the wave field in a north-south vertical section and see the effect of the 3D model of the wave on the wave propagation. And if we now try to fit data with synthetics at 3 different stations, results are very, very contrasted. In fact, the fit is quite good for surface wave between 5 and 10 seconds. And you can see this on the first 4 lines of the figure on the right part of the slide, but it's not good at all between 2 and 5 seconds. And you can see that on the last 3 lines of this same figure. And you can see very large phase lags, for instance, for the relay waves. And here clearly this is an effect of the model, because the Caviani model is not built for high frequency wave propagation. Furthermore, at low frequency, that means between 5 and 10 seconds, the scaling factor we use in order to obtain a good fit in amplitude between the synthetics and data is very different from the one that was obtained by Ford and collaborators. So finally, our empirical correction factor to obtain a good approximation to go from above ground to underground displacement is really different, and here too this is an effect of the frequency, and we have to work on that topic, in fact. So to summarize, when the operational seismic methods bring robust results that are current with that of other technologies, for instance, for the yield for the Beirut explosion, we have to work on the seismo-acoustic coupling, especially at low frequencies, and we have to be aware of the difficulties to work with 3D seismic modeling, especially in an operational context.
Thank you. Thank you, Laurent, for the presentation. Very interesting. I feel that we have no time for questions right now, but maybe at the end of the session, if we have time, we can pass on some questions. Bosche will collate them and collect them. So at this point, we can go on immediately to the second presentation, which is by Chandan Saikia. Please, if you could please play it.
Good afternoon, and welcome you to my presentation on the yield estimation of August 4, 2020 Beirut explosion. I would like to thank my co-authors for their contributions to this presentation. We also thank Dr. Samuel Rigby for providing his blast wave data to augment ours. Beirut explosion affected in so many ways in terms of human life and property damage. It created a huge crater at the detonation, its depth being widely reported at about 43 meters. It generated both seismic and shock wave data. Seismic data at stations towards Cyprus included the hydroacoustic phases. The motivation here is to analyze both seismic and blast wave data separately and estimate corresponding yields. We will report our results as is, with no additional corrections for the surface to the ground coupling of the seismic waves, which definitely is present. These are the topics on the blast and seismic wave analysis that will be presented in sequence. Introduce the blast wave data, discuss signal characteristics of seismic waves, present method used for the shock wave data analysis. We will discuss seismic wave data, where we examine spectral characteristics and investigate if seismic data give any source corner frequency, yield estimates, and then summary in that order. Also, these are reported MB values, and we will be using them to estimate yield using the relation for low attenuation published by Bowers and his group in UK as one of our goals. The magnitude spread here in this table is from 2.9 to 3.6. These are blast wave data taken from the social media. Of all the parameters, we used only the shock wave velocities and distance, where travel times were obtained by analyzing many frames, each frame lasting over 30 milliseconds. The table shows distance versus travel time data for these blast wave that were estimated in this study. We'll further augment this data by adding additional data provided by Dr. Rigby from UK. These are all stations that recorded seismic data that were examined. Note that signal to noise ratio of the seismic phases were best in the frequency band between 2 and 7 Hz. To all these stations, the P wave travel with a speed of 6.5 km per second or slightly high. Hydroacoustic wave travel with a velocity of 1.5 km per second. Here is a display of seismic wave propagation along different paths. Towards the north, mostly dominated by the noise, except for that regional earthquake in the infrasound arrival range between the markers T4 and T5. T3 marker represents the hydroacoustic arrival. For station to the south, P waves dominate. Only at AMAG at 269 km, we see some signals at T3 marker. But other phases similar to this also are arriving at the later time. This suggests that these are probably from some local events. All stations towards Cyprus display dominant hydroacoustic waves. Note that stations ALEF and AKMS, where hydroacoustic phase is not observed, are stations on the far side of the island. This slide is even better. Station CY303, the representation of the wave propagation to Cyprus, and both GHAJ and HRFI to the south along the crust. We plotted both raw and instrument-corrected velocity waveforms to show that they match fairly well. Hydroacoustic waves are highly visible for the propagation through the water and are missed completely at the stations to the south. This shows our spectral analysis. We find that stations to the south have higher P-wave spectral level compared to the level displayed by the station towards Cyprus. The long period level below 1 Hz in the right panel is mostly due to noise. Process this spectra very carefully, extracting P-wave 10 seconds before the P-wave onset and ending 20 seconds after. Noise window had the same length and was from the pre-P-wave arrival. Noise spectra was subtracted from the signal. Spectra were corrected to a common distance of 2 km, but no correction for the attenuation was made. While the overall spectral character is mostly stable at all stations, levels are different for stations between south and those towards Cyprus. This is a display of identically processed spectra for the hydroacoustic phase versus the P-wave recorded on the same seismogram. As in the P-wave, hydroacoustic spectra, especially bracketed within the blue ellipsoids, looked similar, but the spectral level of the hydroacoustic phase suggests a higher level by more than a factor of 10. Of all stations, station GEM is the closest and is about 77 km from the explosion towards south. We'll concentrate mostly on this waveform later. We analyzed blast wave data using Cooper et al. Formulation. We applied the method to both our data and also separately by adding Dr. Rigby's data. Rigby et al. Used a different formula which was developed based on using experimental data published for many hemisphere of TNT equivalence within 1 to 400,000 kilograms. These are the formula taken from Cooper et al. Of the reference below and were used in the study. We used the scale shockwave velocity versus scale distance in our final analysis. For a chosen yield, we converted the distance to scale distance through the FD dependence and the travel time to scale travel time using both FD and FT, where they are given by this formula. Note that the observed to reference pressure ratio is approximately equal to unity because the reference pressure is at sea level and the explosion was at the sea level also. The observed to reference temperature ratio is 1.0521 based on the reference temperature of 15 degrees Celsius and Beirut temperature at about 30 degrees Celsius on the day of the explosion. Top two panels are for the analysis done using our limited data. 4 panels in the top left exhibit the fit in the scale parameters for different yield values. Top right panel shows the limits on the yield for shockwave velocity and distance dependence, bracketing the observations. This resulted in a yield of 600 tons. By augmenting our data by adding Rigby's data and reanalyzing the two datasets together, resulted in a yield of 380 tons with its 90% confidence limits extending from 213 to 619 tons. We present results of this analysis in the lower two panels. This is an attempt to establish the corner frequency of the explosion by carefully examining the nearest station data at 77 km to the south of the explosion. We examined its P-wave velocity and displacement spectra to identify the corner. Looking at the omega to the power -2 decay of the high-frequency spectra above the corner, we can say that the attenuation effect must be small. We identify corner to be at 1.6 Hz with some uncertainty. The explosion being at the surface, we needed to confirm if this corner will stay the same if the explosion was contained. To do so, we estimated the corners using waveforms from tarantula chemical shocks detonated above and below the surface. Their epicenters at 1 meter of each other. We found that the corner frequencies to be indeed similar. This was very important as we wanted to find out what kind of yield would be needed to fit the GEM spectral corner when we make the Beirut explosion a contained explosion. We do not use spectral level, although this may be a key parameter too, but there is too much uncertainty in the surface to the ground coupling of this size of explosions. We are still investigating the validity of this assumption on the source corner frequency. For the rest of the analysis, we will use the Mueller-Murphy source, and we acknowledge that the use of Mueller-Murphy source may have some limitations. This is indeed a literature survey to find the emplacement condition prior to the occurrence of Beirut explosion to be used in the corner frequency analysis. The star shows the location where the explosions occurred, and the prospecting study indicates that the P-wave velocity in the source region prior to the explosion is around 4,500 to 5,000 meters per second. By looking at many post-destruction picture uploads in the internet, I think these values may be high. So whatever value we use certainly has some level of uncertainty. We used 1.6 Hz as the corner frequency of the Beirut explosion, which resulted in a chemical yield of 1.7 kT. It is likely the actual corner is smaller, and because of the lack of data, it is our best estimate. Our assigned uncertainty, which is plus minus 0.3 to the corner frequency, gives a yield range from 1.1 kT to 2.4 kT, but we believe the upper bound in the corner frequency should not be 1.9 Hz. While applying the Mueller-Murphy source, we use the basic scaling rule as the rule of thumb for the depth of burial. Especially we did this because of the lack of data from many explosions of this kind. Without the rule, the depth of burial becomes too arbitrary a parameter, but it is a topic of further analysis. Because of the lack of data, the surface blast wave to the ground seismic wave coupling is also quite uncertain, and so we did not use the spectral level in this analysis. We also used MB values presented in the table earlier to estimate each yield. We used MB versus yield relation of Bauer and his colleagues, which suggested that its chemical yield may vary from 8 to 68 tons. In summary, blast wave data suggests that the Beirut explosion has a yield of 380 tons with upper and lower bounds at 213 and 619 tons respectively. The MB versus yield relation suggests each chemical yield in the range of 8 to 68 tons. Corner frequency versus yield relation suggests a range to lie between 1.1 and 2.4 kT. Overpressure analysis conducted at APTAC by other colleagues indicated that yield is 350 tons. Thus, we have a wide range of variability in these estimated yield values. Finally, in this corner frequency versus yield study, we did not permit the spectral level to play a role because of the lack of ground truth knowledge on the surface blast wave to ground seismic wave coupling. We are analyzing additional data to firm up this coupling factor between the surface versus contained and low versus moderate size explosions based on our own and other investigations. Continued study will incorporate this coupling effect. On behalf of my colleagues, I thank you all for listening to our presentation, and comments are welcome.
Thank you so much, Chandra. Very interesting presentation. Are there any questions from the audience? No. There is one question from my side regarding the hydroacoustic phases to detect on the ocean bottom seismometers. Do you assume actually that the hydroacoustic phase is launched in the water directly at the source, right? Even though it's in shallow water? Oh, you're muted. Chandan, you need to unmute yourself.
Sorry about that. Yeah, I heard your question. Yes, we thought that it is generated, converted right at the continental shelf there, as you explained that continental shelf is going to vibrate and it will go at the wave. But in other case, your super channel was almost at the horizontal level to the wherever the interaction from that source to the receiver. In this particular case, our hydroacoustic stations were down at about 2.5 kilometers, something like that. And so the wave definitely going to the water layer, and the propagation path can be different. And where exactly that interaction happening from the source to the water layer is not, and we are still analyzing that. And also, since it happened on the surface, that explosions, I think there was some conversion from P to S at the surface. S may also convert to some P right at the source, so they can come all together slightly delayed your S to P conversion at the interface. Those things are happening in wave propagation phenomena.
Yeah, thank you, Chandan. Thank you so much. And at this point, we are ready to go immediately into the next presentation, which is by Christoph Pilger. So if I can please ask my colleagues to play the video.
This is a multi-technology analysis of the 2020 Beirut explosion using 3 different observational approaches to remotely estimate the explosive yield. My name is Christoph Pilger, and this presentation is given together with my colleagues from the Federal Institute for Geosciences and Natural Resources, BGR, as well as the German Research Center for Geosciences and the Christian Albrechts University of Kiel. A huge accidental explosion happened in the city of Beirut, capital of Lebanon, on the 4th of August 2020, around 1808 local time. The reason was the combustion of about 2,750 tons of ammonium nitrate stored in a harbor warehouse. It was followed by a huge shock wave due to the explosion. This led to thousands of casualties with more than 200 fatalities and an immense damage to city buildings and infrastructure. Following the explosion, local authorities conducted on-site investigations. Anyhow, there was only limited access to the site of the explosion due to the heavily damaged area and the timing in the SARS-CoV-2 pandemic. Thus only sparse information and data from the explosion was available. We therefore present an independent third-party estimation of the yield of the explosion from the analysis of publicly available seismic, hydroacoustic and infrasonic waveform and satellite radar remote sensing data. We analyzed data from 24 seismometers in up to 400 kilometers distance to the explosion. It is publicly available data from the geophone and iris networks. We identified seismic, hydroacoustic and infrasonic phases clearly separable by their individual wave velocities. They are color-coded in the waveform plot and station map here. Seismic body and surface waves are dominantly observed north and south of the source, while hydroacoustic phases were identified in ocean bottom seismometers of the eastern Mediterranean Sea. An infrasonic waveguide generates detectable acoustic signatures at stations located on Cyprus. Using these distributed stations, we were able to perform a first localization of the acoustic source by a grid search and linear regression method. It is in close spatial and temporal distance to the ground truth event. This investigation is complemented by a moment tensor inversion to identify location, magnitude and yield of the explosion. A moment magnitude of 3.47 results in a first yield estimate of about 1.08 kilotons of TNT equivalent. An independent lower limit estimate of the yield using a remotely quantified body wave magnitude of 3.2 from the reviewed event bulletin at German IMS station PS19 is provided by 0.13 to 0.34 kilotons of TNT. We next investigate the long-distance acoustic propagation and detectability of the explosion in IMS infrasound arrays up to 10,000 kilometers. Detections were found at 5 arrays in Tunisia, Germany, Ivory Coast, the Azores and Cape Verde Islands. Waveform beams and the time-frequency analysis of the explosion using the progressive multi-channel correlation method are shown for 3 stations here. These are used to derive the back azimuth direction, color-coded here, for source localization as well as the signal amplitudes and periods for yield estimation. We perform the source localization with the IMS infrasound arrays using a grid search algorithm and a subset of the 3 best detecting stations, as shown on the previous slide. The resulting source location by stations IS-26, 48 and 17 in distances between 2,400 and 5,200 kilometers is around 44 kilometers from ground truth, shown by the square representing a maximum of the probabilistic density function in the picture on the right. To estimate the explosive yield, we also utilized data from the 3 best detecting stations and applied 2 empirical yield relations, one using dominant signal period and one using wind-corrected amplitudes. The station average yield estimates are 0.86 and 1.06 kilotons of TNT equivalent. We also applied a third independent technique to identify the impact of the explosion and to estimate the explosive yield. Interferometric synthetic aperture radar data from the Sentinel-1 satellite is used to identify differences in the spaceborne images before and after the explosion, indicating and quantifying the building damage. We quantify the difference or the loss of coherence of the images as a relative damage proxy, pixel by pixel, as depicted on the lower right here. We then compare this relative damage to the expected damage following a damage classification. We link the INSA-derived damage maps to overpressure simulations with the so-called boom equation and assume a relation between and certain overpressure values, as shown in the table. The damage of a number of prominent buildings in Beirut, as reported by media after the explosion, is used as ground truth to calibrate the method. This building information is shown as vertical lines in the figure here. The colored horizontal lines represent the satellite-derived damage information, and the curves represent yield estimates derived by the presented method. A best-fitting yield estimate of around 0.8 kilotons and an upper limit of about 2 kilotons of TNT results from this procedure. To summarize our study, we investigated seismic, hydroacoustic and infrasonic waveform signals, as well as a damage estimation from INSA satellite remote sensing data. We located the event with an accuracy of 44 kilometers using infrasound arrays of the International Monitoring System and an accuracy below 1 kilometer, including regional seismometers. We quantified the explosive yield from seismic moment tensor inversion, from infrasonic yield relations, and from an INSA damage estimation. We derived consistent best yield estimates of 0.8 to 1.1 kilotons of TNT equivalent for all 3 methods, with lower and upper boundaries of uncertainty around 0.13 to 2 kilotons of TNT. Using open access data and 3 different types of instruments and methods allowed us to reliably identify, locate, and characterize the explosion. This involves sensors from the International Monitoring System of the CTBTO, as well as additional national technical means. It demonstrates fulfillment of the IMS design goal to detect any explosion with a yield around or above 1 kiloton of TNT equivalent. You're welcome to find further information in the related publication. Thank you for your attention.
Thank you so much, Christoph. Very interesting presentation, also with the remote sensing data. We have some time and we have two questions for you. So the first one is from Francois Schindelen. How do you reconcile your estimate with that recently published by other teams, which suggests that energy should probably be less than 1 kiloton on the basis of spectral analysis of waveforms?
Oh yes, thank you. That's a good question, and there, of course, already has been quite some discussion, since there is at least half a dozen different approaches to estimate this explosive yield, at least shown in this conference. And well, to estimate this, again, it's the choice of the methods that are different. As far as the presentations given here, the seismic method applied by CA colleagues, for example, includes a different set of prerequisites and assumptions, and so this might also be the case of the different outcomes. So, for example, the 1D and 3D models that I used, and well, also the input that is given shown by different body wave magnitude estimates. So we choose a 3.2 estimate, and we have seen that there are estimates between 2.8 and 3.5. And this leads to a certain range of uncertainties. This is, of course, clear. And I think, which will also be stated in our final publication about this, the total range, including all the uncertainties from our estimates, is between 0.13 to 2 kilotons. And well, this is probably more in agreement with the estimates from other teams.
Thank you so much, Christoph. And there is a second question from Islam Hamama. How did you apply the Ravel 1997 equation for meteor yield estimation in this case? And does this relation give you results higher than the other yield relations?
Oh yes, thank you for this question. Thank you for this question. Yes, indeed, the yield is somewhat higher. This FTEC method, originally used for bolides, so for elevated explosive sources, is an approximation to use it for a surface explosion. This is the first part. So it's not the same as an explosive source at altitude, where the energy radiates in all directions, spherical. And yes, the explosive yield is somewhat higher. It was the upper number of 1.06 kilotons, and the wind-corrected amplitude-based estimates are somewhat lower, to 0.8 kilotons.
Thank you. Any other questions? No? So, well, a question and some comments maybe from my side. So, speaking about the infrasound source term, precisely because it is so near to the ground, are you then assuming something like a dipole radiation pattern or something like that?
No, not especially, but it depends on the method that we choose. So well, the infrasound estimates, the empirical yield relations, they at least the amplitude-based one by Los Alamos takes into account that this could be surface explosions. It was used for other surface explosions, like the Buncefield explosion or others. And well, as already stated, the other assumption is also used for bolides. And well, this should take into account that it's a source normally at altitude and having a radiation pattern in all directions.
Yes.
And on the other hand, the seismic some of the seismic methods are also applied for underground nuclear explosions. And in this case, it's a surface explosion that only couples into the subsurface. And yes, there's of course some uncertainty in these assumptions.
And thank you. You're saying a keyword here, which is uncertainty, and we will have even a panel about communicating uncertainty tomorrow, because I think that these analyses of this event precisely show how many uncertainties there are in the boundary conditions, in the properties themselves, although there's good knowledge about the local tomography from the geoacoustic or from the geophysical surveys for oil exploration. But there are so many uncertainties that add up and give you then such a spread of possible yields in the end. It shows how complicated analyzing such an event really is when you need to try to quantify to get a quantitative result for the yield. But yes, very interesting. Thank you. And at this point, we are ready to go on to the next presentation, which is going to be delivered live by Mohamed El Gabri from Egypt. And we are going to do it like this. We will play the slides from here. And Mohamed, welcome. You please let us know when we need to flip to the next slide. And then
is it possible to share my screen? I already shared.
Oh, you are already sharing it. Oh, so there's been a change. Good. Yes, let's see if it works, and hopefully the video works too. Yes.
Yeah.
Thank you
Okay.
so much. Please.
Thank you, Mario. And it's quite challenging to be the last speaker in a session. Most of the speakers has talking about the same subject. I hope I will not be so boring, and I will try to go fast where areas which has been mentioned before, and maybe keep some time for discussion. Of course, in the 4th of August 2020, there was a large amount of ammonium nitrate has made a strong explosion, causing a tragic accident in Beirut. You can see here in the video the flashes, which is the problem was having a firework stored in the same area with the ammonium nitrate. And the ammonium nitrate doesn't ignite by itself, but it needs a good condition in order to explode. And that's what had happened in our case, where the firework has been ignited and set the condition for the ammonium nitrate in order to be exploded, as you can see here. The explosion has been very violent. Once the reaction sparked, the ammonium nitrate exploded violently, producing a sudden strong flash, and being at the beginning of the explosion, the solid ammonium nitrates decomposed very hastily into gaseous nitrous oxides and water vapor. From visual images here, you can see the water vapor clearly distinguished from the brownish nitrates, nitrogen dioxides in background. And you can see here how the pressure wave was very destructive and traveling through the buildings of the area. We have used different data sets in order to analyze this event. As the previous speaker, we have used Sentinel images, but we have coupled both Sentinel-1 radar data and Sentinel-2 multispectral imaging, including visual and near-infrared and shortwave infrared, in order to analyze the area. And we have come up with 4 areas of threat destruction: the center of the explosion itself, and there is half circle because of the other side is the sea, which has been heavily distracted, and the C zone, which is heavily to slide damage, and then the slide damage in the D zone, and then no damage outside the area. We have an area of a circle of around 1.5 kilometer. In 1 kilometer, many of the buildings were totally distracted. our data is correlated with reports from the field about the destruction observed. The explosion has triggered seismic, acoustic, and infrasound signals that propagated through the lithosphere, atmosphere, and hydrosphere. The signal was widely recorded in the neighboring countries and even in the case of infrasound being reported regionally. The explosion signal has been recorded widely in Israel, occupied Palestine, Cyprus, and Egypt. The nearest seismic station was GEM, open access seismic station was GEM. It's about 77 kilometers, while the farthest station with a clear seismic data was NDB3 in the Egyptian National Seismic Network. Seismic record has shown different phases where P wave is recorded as a first arrival, in addition to having the T phase, which is recorded here, and the shock wave. When we look to the travel time curve, it is clear that we have the P wave with velocities around 6 kilometers per second, and then we have the T phase, which around 1.5 kilometer, and at last we have the phi shock, the shock waves. It is quite interesting.
Mohammed?
Yeah.
Sorry, you are actually sharing on the screen sharing your presentation, including the notes. We can see it fine.
Yeah, I can
okay
share the other one.
Yes, if you like, up to you. I just wanted to let you know.
Yes, it's screen 2.
Yeah, now yes.
Is it better like that?
Yes, now we see the big presentation. Okay,
Okay.
thank you. Thanks.
I'm sorry for the mistake.
No worries.
Okay, you can see here the shock wave, which is recorded and from different stations. If we looked, one of the station which has recorded all the 3 arrivals, the seismic, the T phase, and the shock wave, was in Cyprus, ASGA in South Cyprus, and it's very clear that the energy of the signal is very different here. The seismic signal energy is not comparable to the T phase and the shock wave. Another station to the north of Cyprus as well, where we have all of them. What was interesting for me to look to these 2 stations, one is the ocean bottom seismometer in Cyprus here, where you have the seismic wave and then the hydroacoustic, which is clear. And the other one was to the Mediterranean coast of Egypt. It's about 727 kilometers away from the site, where still we have the T phase is clear at the same, almost the same frequency. It's, of course, the energy is less, or we having higher, and we having higher noise. The station is around 15 kilometers away from the 10 kilometers away from the coastline. We tried to track the phase in stations to the west, but unfortunately there was an earthquake in Turkey, 4.4 earthquake, which has contaminated the record, and we couldn't identify the signal further west. Coming to the yield, we have applied 2 relation depending on the conversion of ML to the yield, Gitterman and Haltron 98. And both relation are from the Middle East explosions, and they are comparable. We have the ML is the yield or TNT equivalent yield is ranging very much in 22 stations in Egypt and in the whole region. The equivalence was around 280 ton of TNT. If we used the report of GHD 2012 about the equivalence of TNT to ammonium nitrate, we find here if it is stored in bulk base, which was the case in our case here, it's ranging from 15 to 32%. So our 280 kiloton, if we convert it according to this relation, it will be around 1.8 kiloton of ammonium nitrate, which is we find it more reasonable because we know that it was 2.7 kiloton was stored in the port at that time, and this is quite comparable. If we look to the infrasound record, we have here the infrasound propagation. There was a strong jet stream towards the west, especially in the stratosphere layer, which is considered as the main layer in the infrasound propagation for long distance. In this figure, it shows that 2D transmission loss using normal modes. So the areas where it is quite red, we don't expect to have record, and areas with greenish, we expect to have record, and this was the case, having 26, 48, 42, and 11 the record. In addition, we were by a chance testing one infrasound sensor in our office here in Helwan. It was a single station without noise reduction system, but it recorded arrivals from the signal. These are the profiles. Again, the 2D loss simulation of parabolic range-dependent propagation methods, the direction of I-48, I-26, and I-17 respectively. By checking the celerity, which is the ground-to-ground speed, it is ranging from 290 meter per second to 310 meter per second, which is comparable to the speed which calculated even to the shock wave in seismic station. And it confirms that the reflection was from the stratosphere. Here we can see the records from IMS stations, and this is the Helwan station, where I don't consider it a station, it was a sensor under testing, and we see here the signal at the expected arrival time. The 3 IMS station records the event as expected. The shock wave is recorded in the station with distance ranging from 212 to 316 kilometers from the epicenter. There is no signal recorded before the 200 kilometer, which is acoustic shadow zone, which is expected. After 316, there was weak, we expect it was weak to be recorded, or maybe it was contaminated as well by Turkey earthquake. As you can see here, there's 3 recording from the IMS station, and it's very nice to look to this recording of I-48, where we have multiple reflection over the Mediterranean is very clear. Of course, reason for that reflection is quite interesting to be studied. To conclude, using the open access data and the Egyptian National Seismic Network, we have recorded the shock wave in distance up to 316 kilometers and hydroacoustic signals, T phase in the 727 kilometers. Average magnitude from 20 station was 3.6 ml. Estimated TNT yield was from around 200 to 230 tons, while ammonium nitrate equivalent yield is ranging from 1.9 to 2.3 kiloton according to the GHD relation. Event is very interesting event as a ground truth event for IMS, especially infrasound detection. And we need to further investigate and further understand the T-phase signal which was recorded during this event. As I thank you for your time and ready for questions.
Thank you so much, Mohammed. Very interesting presentation as well. There are no questions from the audience right now. Oh, yes, there is one. One moment. So we will pass it on. It takes a moment to copy it over so we can see it. Okay, from Jan Kano. Mohammed, I do not notice the offset between your infrasound sensor in Egypt and Beirut source. So can you repeat what the offset was between the sensor that you were testing in your laboratory?
You mean the distance?
Yes, I think that's what they mean.
Yeah. So I can get it from the table, but it's around 600 kilometer, but I can't check it exactly.
Okay, thank you. Any other questions? No? From the other speakers, from the other presenters, is there anybody who wishes to ask a question? I have a question for you. When you recover from the say TNT equivalent yield estimate, you compute back to how much ammonium nitrate it could have been, and that the upper limit of that is 2.3 kilotons, whereas you said that it's apparently about 2.8 kilotons that were stored in that location. So would you think that this difference could have to do with the state in which the ammonium nitrate could have been after having been left there for a very long time and maybe igniting less efficiently, or in general that maybe not all of it might have exploded?
I would go for your comment previously about our understanding for the geophysical model in the area. Okay. Maybe it's because of our poor understanding. Of course, maybe because it was stored for very long time in a very poor condition with high humidity near to the sea. We expect part of it was not ignited, but also we need to enhance these events. Is very important in our enhancing our understanding to our geophysical models and in our region, and it is really needed.
Thank you. Any other of the speakers that would like to ask a question? No, nobody. Any question in general about the talks in the session that anybody wishes to ask? Also, if any of the audience listening in to this session wishes to ask another question. I think there was one that was remained unanswered from one of the previous presentations. It was about the duration of the T phase, I think. If you go down, no, down. No, this one, Thomas van der Mark. Yes, that was relating to the DPRK 6 detections with the hydro station. Can you comment? That's from Thomas van der Mark. Can you comment on the duration of the T phase from the test event compared to T phases from natural events? Was it shorter? Yes, indeed. That's one of the things. You can see that they are much shorter, and you can see that also, for example, I think in the presentation that you had, Mohammed, that when you see the T phase, it is rather short in duration, whereas T phases from natural events are much longer. There is a question from Mohammed. The lineup of stations in yield estimation is sorted according to azimuth. If not, would it imply some sort of directivity? You're muted, Mohammed.
Yes, we have some sort of directivity in this event. Again, we are our understanding to the attenuation for seismic waves and the distance, especially we are near to the Dead Sea fault. Some stations are crossing. We have subduction area. It is very complicated tectonic area, and we need to better understand it. yeah.
Thank you. So this question was from Karl Koch, and now we have one final question from Martin Kalinowski from CTBTO, and he asked if the presenters can perhaps summarize what the CTBT expert community learns from the Beirut explosion to enhance nuclear explosion monitoring. Please, who wishes to start with the comments? What can we learn from the analysis of the Beirut explosion that can be used to enhance IMS CTBT monitoring?
I can volunteer to start.
Yes, please, Mohammed.
Okay. For my understanding that the scaling relations and the yield relation need to be more studied, and we need to develop more physically based relations. There is a lot of historical events, and we have a lot of fitting relations from data available, but also we need to go for modeling and numerical modeling to better understand the mechanics and the yield, and to compare it to the observation. I think this is very important.
Thank you. Any of the other speakers would like to add something?
Oh yes, I could add something for the station component. It has been seen that using the IMS network, for example, using the infrasound stations from distances of many thousands of kilometers, introduces some kind of uncertainty, of course, again, in the location, in the estimation of yield, and in different parameters. And we have seen that using regional seismometers, many of the groups did so, optimizes the location estimation down to kilometers, a few kilometers or a few seconds. And this also opens other routes, so including regional seismometers or satellite data, to have further estimates, further tools for estimating the yield, for example.
Thank you. Yes, maybe one last question from Stephanie Noskaman, and I think that this one is for Christoph, I think. On detecting underground cavities due to UNEs using seismic ambient noise, is there an understanding of the limits on cavity depth from the surface or cavity size which can be detected from this method?
Yeah, this is a very good question, but right now we cannot answer this question. We don't know, because we had only this one test in the Felsőpeteni in Hungary. Now we would like to apply this method for other sites, and we will see. It has to be checked.
Okay, thank you very much. So great. I thank the speakers and the authors for very interesting contributions in a session that was varied, showed various analysis methods and technologies, and was quite fascinating. And I do thank also the audience for very interesting and engaging questions. So thank you so much, and this concludes the session. Goodbye.